For our final set of topics, let's talk about multiple integration. So we're going to start by talking about iterated integrals. Let's look at the following example. Find the integral from 0 to 1, 0 to 2, x plus y, dy dx. So you always work outwards, or start at the inner part and work out. So here, the first thing you're going to look at is this integral. You're going to integrate with respect to y. So you're going to view x as a constant. So you're going to get x times y plus y squared from 0 to 2, and you're going to plug that in place of y. So you'll get 2x plus 4, and if you plug in 0, you'll get 0. So then I just now need to integrate this single integral, x squared plus 4x from 0 to 1. If you plug in 1, plug in 0, you get 0, so I'm getting 5 for this integral. Let's look at one more of these. So let's look at find integral from 0 to 1 and 0 to y, 6x plus 5y cubed dx dy. So always on the outside of your integral, you're going to have constants here, but now I have variables on the inner ones. And if you notice, the order of my integration has changed. So now, if I'm working inwards to outwards, I first need to integrate with respect to x. So I'm going to compute this. So you're going to view x as being your only variable. Then if you have y, it would be a constant. So you'll get 3x squared plus 5y cubed x. And x goes from 0 to y. So now I have the integral from 0 to 1, 3y squared plus 5y to the 4th. If you plug in 0, you'll get 0 in both places. So now I'm integrating with respect to y. This will be y cubed plus y to the 5th from 0 to 1. 0, they're both 0 because it's polynomials, so my answer is 2. So now let's talk about polar coordinates. So sometimes it's useful when you are calculating these integrals to switch to polar coordinates. So let's look at an example. Find a double integral over r of y dA, where r is the annular region lying between the two circles. X squared plus y squared is 1, and x squared plus y squared is 5. So if I draw this region, right, this is the equation of a circle of radius 1. Here's my circle of radius 1. This is the equation of a circle of radius square root of 5. Square root of 5 is a little bit bigger than 2. So here's my circle of radius square root of 5. ignore the fact that these are not the greatest looking circles. So I'm looking at the region between these, so that's that region. So here, because I'm working with circles, polar coordinates makes a lot of sense here. So I'm going to describe this region in polar coordinates. R is between 1 and square root of 5, and theta is between 0 and 2 pi. So now what I want to do, so I'm going to set up my integral in polar coordinates. So remember, we're looking at the integral over r y dA. So you're going to switch, so theta goes from 0 to 2 pi, r goes from 1 to square root of 5. Now you have to switch y into polar coordinates, but remember y is r sine theta. So this will be r sine theta. And then when you're switching to polar coordinates, you get an extra r dr d theta. So now I'm getting the integral from 0 to 2 pi, 1 to square root of 5. This is r squared sine theta dr d theta. So the first thing you're going to do is integrate with respect to r. So you're going to get r cubed over 3 sine theta. So then you're going to get the integral from 0 to 2 pi, and it's square root of 5 cubed over 3 sine theta minus 1/3 sine theta d theta. So if you want to, you could factor out a sine theta, and if you did, you would be left with 5 square roots of 5 minus 1. And then you can pull that coefficient out, and you're just integrating sine. The integral of sine is a minus cosine. And then you plug in top number minus bottom number. So minus cosine of 2 pi minus a negative plus cosine of 0. Well, cosine of 2 pi is 1. Cosine of 0 is 1, so you're going to get 0 here. So sometimes it's beneficial to switch to polar coordinates. Now let's talk about surface area. And I'm just going to go over the formula to set up. When you're finding surface area, it's the double integral over your region R, 1 plus the partial derivative with respect to x squared plus the partial derivative with respect to y squared dA. So you should look back at some examples that we did in that section, but we're going to continue talking about triple integrals in our next video to finish out this section of material.